On the left, we've got the list of notebooks, and the one that you'll want to look at to follow along is the one called Cube Analysis Webinar Solutions. And there's that to give us some more room. All right, so as I mentioned, we'll be taking the simulations, a small part of the simulation, and that's from an MRS simulation of Galaxy NBC 5728, and it's a small bit of it at about 11 microns. It's one of the subbands. We're going to demonstrate how to load that data from a notebook cell, adjust display parameters, and then subtract continuum and make some moment maps. The first cell you want to run is the imports. We need JWBiz to get the Cubeviz tool. And we also use some AstroPy functionality to read data sets into the notebook. Then the next cell you want to run is this one that says Cubeviz equals Cubeviz, and launch the Cubeviz application like so with the shift return. And you'll see the various viewers that we'll be using for Cubeviz, and I'll explain the various parts of this tool. You can also look back at the JWebbinar 2 notes and presentations on more functionality for the tool. As we're going through this, you will want to follow the UI instructions, which are right below the Cubeviz application. And we're going to start with task 1 and load the cube from MRS. And to do that, go down to the next cell, which is load science data cube into Cubeviz. And that reads a file from box, which is this MRS data cube. Going back up to the tool, you'll see the cubes load into the viewers. And in the upper left-hand viewer, which is a cube viewer, all the top 3 viewers are cube viewers, but you can also use them to look at 2D images. So we want to adjust the stretch by clicking on these slider tools. And when scrolling down to where it says stretch, motion from linear to logarithmic. And we can also change the percentile per stretch to 95% or so to see the wings of the PSA. Once you have that there, the middle browser is actually for the uncertainty cube, the air cube, and the right one is for the data quality cube showing masked or bad pixels. And then as we slide through the cube using the slider at the top, you drag it and you see all 3 cubes and slide through the different slices together. Okay, so that's the basic loading and display of a cube. And what we want to do next is demonstrate how to select a spectral region for further analysis. So whenever you want to create a new region in one of these tools, you just go up to the top bar where it says no selection, create new, and you can click on that. That's the default, but if you have multiple regions already defined, you're going to want to switch between them using this tool at the top. So what we're going to do is select a wavelength range in the bottom spectrum viewer. And to do that, what you want to do is click on the hammer and screwdriver icon, which is on the right side of the spectrum viewer, which is the bottom viewer. And you'll see some tools pop up. On the left, we have some pan zoom tools, and the home will return to the original zoom. The region selection tool that you want to use is the silver blue rectangle with the dots in it. Click on that. That tool is activated, and you can now select a feature such as this 10.5 micron PAH dust feature that we're selecting. It will be highlighted, and in order to see that better, you can go to the display tools again, this time for the spectrum viewer, and select the red square, which is the subset that we selected. And we're just going to bump up the line width a bit so that you can see that a little bit better. And whenever you want to get out of one of these menus, all you need to do is click somewhere else, like on the top blue bar in the viewer. So now we selected a spectral range, and what you typically want to do is perhaps make an image of this region, and we're going to use the moment maps tool to do that. There's a number of tools that you can, data analysis tools that you can access. In the upper right corner, there's this Lego icon with a plus, and that's meant to represent plugins, which just means that there's various data analysis tools that can be plugged in here to add additional functionality. And you'll see we have Gaussian smoothing, collapse, model fitting, unit conversion, line lists, plotting, line analysis, and moment maps. We'll be focusing primarily on the moment maps functionality here. Okay, so we've specified a spectral region in the spectrum viewer, and we want to operate on it using the moment maps plugin, which is on the right. And often for these data analysis tools, you want to resize that tray so that you can actually see the text without it wrapping around. And it'll resize the other viewers as well. First of all, we want to specify the data set. It's already by default selected the whole science cube extension of the data set we want. So it's already what we want. For the spectral region, we'll want to click on the right arrow and select subset 1. So that's that red spectrum that we selected, that region we selected on the left, and the spectral bounds are indicated in the 2 lines below that. And then in order to make an image of this spectral region, all we need to do is at the moment, for moment 0, that's a line flux image basically. Moment 1 would be velocity, moment 2, velocity dispersion. And then you hit calculate, and you'll see that up at the top, that moment map was added to the data collection. And in order to display that, we are going to co-opt this middle viewer here, deselect the error cube, and select the moment 0 map that we just created. So with the display values again, using logarithmic 95 percentile, and also show you how to adjust the color map. So you want something pretty like Inferno, and click on that. So what you see in the middle viewer at the top is the moment 0 map, basically the sum of all the flux in those spectral channels that we selected. Now, we have included both the continuum and the feature in this map. And what we're going to do next is actually subtract the continuum so that we can get a cleaner map of, say, the narrow spectral features of the 11.25 microns. But first, we need to model the data cube, subtract out this continuum and these broad pH features so that we only get the line map. So where we're at now, we are on task number 4, is to model the continuum of the whole cube. So we want to go back again to the plugins tray on the upper right, fan that out a bit. Go to the model fitting plugin. Click on that down arrow. The data isn't selected, so we need to click on that. And what we want to do is model the whole cube, which is the science extension. We can actually select subset 1 as well. And that would model just the region we selected, but instead I want to model the whole thing. Select the science extension. In order to specify model components for fitting, go to where it says model and click on that, and you see all the various possibilities. We're going to add to these as we go along right now. We'll just be using the linear 1D and Gaussian 1D components. So you select the model that you want, and these are actually AstroPi models that are implemented in SpecUtilis. So for each model component, we want to specify a name. We'll just call this L. Add the model to our set of components. We'll also want Gaussian features for the 2 broad dust features that are in the. So we go down and select Gaussian 1D. Call the first one G1. Add it to our set of model components, and also we'll add a G2. So now we've got 3 model components. We want to add them together to a continuum model, and we'll say specify that in the model equation editor as L plus G1 plus G2. We can also specify a name for the model. We'll just leave it at the default, which is model. It's fine since we only have 1 more working with. The thing you need to look at is the tool guesses what, for example, the slope and intercept might be, and also amplitudes and widths and centroids for the line. But those aren't necessarily right, so we have to go in and give them better starting values. And in fact, it's a good idea to fix some of these things so that it doesn't get lost in plenty. So for the first dust feature at 10.5 microns, I gave actually a list of parameters that you might use as starting parameters for this. So I'm going to be using 3.5 times 10 to the 5 megajanskeys per square diem. The units are actually wrong because you know when you sum over an area in the spectrum that you should have megajanskeys instead of per square diem. For standard deviation, we're going to use 1 times 10 to the minus 7 meters. These are all in meters because that's the native units of the data set. You can actually import them in whatever units that you have, including microns or kilometers per second or whatever you might have for your data. And then we want to specify a center for this first feature of 10.5 microns, which is 1.05 times 10 to the minus 5 meters. We're actually going to fix that because it might get confused and try to fit that as a bump somewhere else. And then for the second Gaussian component, we do the same thing, similar thing. And we're going to set the amplitude for that to 1.5 times 6 megajanskeys per square diem. The width as 1.0 times 10 minus 7 meters. I'm going to fix that. This one in particular has some trouble fitting because it has a funny wing on it, so we fix that. And also specify the central wavelength as 1.125 times 10 minus 5 meters, and we'll fix that. Once you've specified your starting parameters for all of your model components and check the ones that you want fixed, we've specified the equation that we want to fit. You just go down and you hit fit. Very quickly, it will fit that one spectrum in the spectrum viewer with its best fit. And like I mentioned, the shape of this pH feature isn't quite a Gaussian, so it's not doing a perfect job. We might want to use a Drude function if we can add that to our models. This doesn't exist yet in the tool. Also, there's probably another pH component over at longer wavelength that we're missing. But that's good enough for our purposes for demonstration. So we fit this function to that one spectrum in the spectrum viewer. Now we want to fit the same function every spaxel in the cube. And to do that, we hit apply to cube, and we'll use parallel processing to fit all of those spaxels. Probably about 900 of them or so that we're fitting. And it only takes about 1 minute or so to do that. Of course, the more complicated your data gets and the more wavelength elements, the longer it will take. Okay, so we've modeled the whole cube, and just to show that, we can go up to the middle panel again. Let me stop this tool tray. And we'll go in and we'll deselect the moment zero map and select the model 1 cube. Then we want to vertical stretch again, logarithmic. Want to make the color map something else. There it is. And the stretch 95%. And you'll see here our model cube. So when we scrub through the cube now, we'll see it scrubbed through the data and the model. And it looks like the model is a pretty decent match to the data with less noise. And you'll notice as you go into the region that we've selected, the spectral region, it turns red. So this demonstrates that the 4 viewers are linked together. They know about where the regions are in all 4 viewers. And that's a nice thing. All right, so we've got our model cube. What we want to do in order to access and get a good moment 2 map of this narrow line over here is subtract it off of our data. So to do that, I've created a notebook cell down below where it says continuum subtraction. And there's several steps in here. But this is a nice demonstration of how, we loaded data into Cubeviz, and now we can take the data products that we generated with Cubeviz and load them back out, do some stuff with them, and then load the new data products back in. And so to do that, first I'm going to just read this cube into the notebook. We had only read it into the Cubeviz viewer. Now this first command goes into the notebook. And then we want to take the model cube that we just created. And the way to access that is you use Cubeviz app get data from viewer. We want to specify the uncertainty viewer, which is the central viewer. And we want what the data set that's called model cube 1. And you can see which those are, those labels, by going up to the Cubeviz data tab. You'll see the one we want is model cube 1, and you have to specify that in the get data. So going back down to that cell, I also print the model cube data structure, and then we subtract off the model cube from the science data, and then we can load that into Cubeviz again using the Cubeviz app load data. So I'll run that cell, and what you'll notice is that I've done an info command on AstroPi fits.io, and you can see the various extensions that are in our data cube, our science data cube. There's the science, the air, and the data quality. Those are the three things that are shown in the cube viewers, and some other information. Also, we have a specification of the model data set that we pulled out, data structure. Okay, so we've loaded that into Cubeviz with that command as well. And you'll notice, let me go back to this to show, viewer, let me change it back to the maximum. All right, so you'll see that this continuum subtracted data set shows up as well now. And we're going to center on that narrow line feature that was on top of the PH feature. The hammer and screwdriver, use the pan tools, pan zoom tools, and you want to select the horizontal arrows is for panning and zooming only in the horizontal direction. Move your feature of interest to the center, and also zoom in a little. We want to do this programmatically to avoid that problem. I've added an extra cell down below where you can adjust the pan zoom to the wavelength region that you want. All right, so we want to do a moment 1 map, which is a velocity map of this narrow line. So we can just go up here and create a second subset. So we go up and click where it says subset 1 and change that to no selection, create new. And then what you do is select the region selector tool and specify that narrow emission line that you want to map. It will highlight it green, and again, it's hard to see, so you can adjust the thickness of a line, the layer tab, subset 2, and boost that up a bit. Oh, no, we don't want subset 2, we want data with subset 2. There we go. So that's the line we're going to be trying to model. I'm sorry, click the moment map up. Okay, so we specify the region, and we just go back over to the tool, moment maps. This time we want to use subset 2, or whichever subset, main subset you selected, and change it from moment 0 to 1 for velocity and calculate. That shows up in the data sets list. You can also save this image as a FITS file. I'm not going to do that at the moment. So we've created our moment 1 map, and we're going to pull it up over in the third cube viewer on the right. We're going to deselect the data sets that you're viewing in that viewer. Select the moment 1 map. You'll notice that it's pretty flat, and that's because it's a point source and there's no gradient in the spectrum across the field. So you can play with the contrast if you want, but you will not see much in this map because the spectrum is pretty constant. All right, so that's it for the MRS dataset. I want to demonstrate loading the IFU dataset, and also an optical data cube from Manga, SDSS, just to show you that you can do that. So if you go down below the continuum subtraction and go to where it says NIRSpec IFU, we're going to launch another instance of Cubeviz, but we have to call it something else. You don't want to say Cubeviz because it's already been used, that name. Call it Cubeviz 2. launch the application again, a different one. You can have as many of these as you want in your notebook. And now we're going to load an IFU data set from NIRSpec. Using the next cell below that. Again, using the upload data command. Click enter. Again, we can adjust the display parameters using the sliders, stretch, percentile. So, and you see the NIRSpec PSF. And you can scrub through the cube and see how that changes the wavelength. And again, there's a number of things that you can do. Same kind of analysis that we did on the MRS cube. Quickly, I will demonstrate doing a collapse, say, over the oxygen 3 line that's redshifted to redshift 1. Plugin tool. The collapse tool is more simplistic than the moment map, but basically it just adds up all of the wavelength bins across the cube. The science cube. And the spectral region that we selected is called subset 1. And you can collapse along the spectral or the spatial axis. So we're going to collapse along the spectral axis, which is 0. Using a sum to get a flux map, band, and apply. We do our middle data, middle viewer, left collapsed data set that we just created. Oops. Okay. And this is a map of the O3 line, the question. And playing with this stretch. So there, we've made a map of the O3 line using a different method of the collapse. So I demonstrated another one of the tools that you can use. Finally, I just want to show that you can get a real moment 1 map of velocity field from a Manga cube, which actually has velocity structure across the data set. So we'll launch yet another Cubeviz viewer down at the bottom of the notebook and load in this file from Box. It's an optical data cube. Scrub through the slices. You'll see that it's actually a galaxy. Won't bother playing with the stretch at the moment. We want to zoom in to the H-alpha feature, and I've actually set up a programmatic zoom on that for the same reason I mentioned before. And this is the H-alpha line in the middle. It's got this double peak profile because of the rotation of the galaxy. So to show a velocity map, a moment map, we go and we select our tools, region, create a subset, and the H-alpha line, and we can adjust it. Okay, so you see we've selected the H-alpha line, and we can create a moment map of that, moment 1 map. And moment maps, flux data set. Spectral region is subset 1, and we'll calculate moment 1. And we'll use the central viewer at the top, select moment 1, and you'll see there's a gradient across the field, and you can see that better if you go in and select a different color map. Blue. All right, so now you see that the moment 1 map actually does give a velocity field